Hello guys, why is the periodic table so awesome? Because the elements in it are arranged in repeating patterns. So if you understand these patterns, you can actually predict the different properties of the elements in the table. And this is called periodicity. So it refers to the repeating trend in properties of elements based on their atomic number and also electron configuration. Here we are going to discuss three trends. The size of an atom and an ion. This is simply the mean distance from the nucleus to the boundary of the surrounding shells of electrons. So basically how big your atom is. Then the ionization energy. This is the minimum energy required to remove the most loosely bound electron of an isolated neutral gaseous atom or molecule. Here is an example. Let's say we have a sodium atom. We are trying to remove one electron. We are going to produce a sodium ion plus an electron. So the energy associated with this process is called the ionization energy. And the third one is electron affinity. This is the energy change accompanying the addition of an electron to a gaseous atom. And what's interesting about electron affinity is that it is an exothermic process. So, for example, when we are adding an electron to a chlorine atom, we are going to produce a negatively charged ion, an anion, and this process is going to produce extra energy. Okay, so how to figure out the trends? Remember this, like charges repel each other, unlike charges attract each other, which simply means that when you have two electrons, they tend to repel each other, right? Because they have the same charge negative, and electrons and protons will be attracted to each other because they have opposite charges. So in an atom, electrons are both attracted to the nucleus, where the protons are, and repelled by other electrons. Okay, so let's put this into practice. Let's take a look at the periodic table. Let's start with the first element, our favorite one, hydrogen. How many protons do we have in hydrogen? One, right? How many electrons? Also one. We can actually use the Bohr model to simplify our representation of different atoms. So let's take a look at the hydrogen atom. Here we have the nucleus, right? Right in the middle, that contains one single proton, and we have on this one shell one single electron. Pretty simple, right? Okay, what happens as I start going down in a group? So, for example, let's go from hydrogen to lithium. Will that atom be larger or smaller? Well, lithium actually has three electrons and also three protons. So this is how it's going to look. Basically, what happened, we added an extra shell. Remember, as we move down in a group, we are moving through the periods. So we are going to have n equals 1, n equals 2, n equals 3, and so forth shells. So it's going to get bigger. So what happens when we go to sodium? Will it be even bigger or smaller? It's gonna get even bigger because we added another extra shell. So now we have three shells. So we can say that as we go down in a group, as this arrow shows, the atomic size is going to increase. Okay? I hope this makes sense. All right. Now, what happens if I start moving left to right across a period? In this case, I am not adding shells, but I'm adding protons and electrons. And because I'm moving within one shell, the electrons will actually feel a larger attractive force from the nucleus as I go across the period. So what does this mean? Let's check out beryllium compared to lithium. So beryllium has 4 electrons and 4 protons. Will it be larger or smaller than lithium? Remember, we are in the same shell. it's actually going to be a little bit smaller because we not only added an extra electron right here, but we also added a proton to the nucleus. Okay, what happens when I move to boron? Will it be smaller or larger? It's again going to be smaller. And then I can move to carbon, which is again going to be smaller. So here is my trend. As I go across a period, left to right, I am going to decrease the atomic size. So atomic size gonna go down. All right, what happens to ions? Let's say that I want to make a sodium ion. What will the process entail? Well, I have to remove an electron. Which electron will I remove? Which one is the easiest to remove if you look at the sodium atom? The one on the outermost shell, right? And how does this happen? Well, it's called ionization. So I'm going to produce an Na plus ion, which is a cation. And because I removed an electron, it's going to become smaller than the neutral element. So from here, we can get to the conclusion that when we produce positively charged ions, we are going to reduce the atomic or ionic size. Now, let's take a look at chlorine, for example. So chlorine is in the same period as sodium. It's right here. It's actually smaller, right? Because it's further away to the right from sodium. Now, what happens if I add an electron to chlorine this way? What type of ion will I produce? I will produce a negatively charged ion, right? And anion, will it be smaller or larger than the neutral chlorine atom? Well, because electrons actually repel each other, it's going to be larger than the neutral chlorine atom. So from here we can make the conclusion that when we are producing positively charged ions, they are going to be smaller than the neutral counterpart. And then when we are producing negatively charged ions, they are going to be larger than the neutral counterpart. Now, what happens when ions contain the same number of electrons? So actually a series in which all ions have the same number of electrons is called the isoelectronic series. And here we have one. So we have O2 minus, for example, right here. How many protons do we have here? So oxygen is element number 8. So we are going to have 8 protons. How many electrons do we have? Well, 8 plus 2, because we have a charge of minus 2, is going to give us 10 electrons. And if this is truly an isoelectronic series, all the other ions are going to have 10 electrons. Let's take a look at fluoride ion. Okay, F minus. It's right here in the periodic table. How many protons do we have? 9, right? So 9 protons, and also because it has only one negative charge, we are going to have 10 electrons. Then Na plus, the sodium ion, it's right here. We were talking about it already. Now Na plus actually has 11 protons because this is an 11th element. And then the magnesium cation, Mg2 plus, is going to have 12 protons. So what do you think? As I increase the number of protons, will I increase or decrease the size of the ions? Actually, as I increase the number of protons, the electrons are going to feel a larger attractive force. So this means that as I increase the number of protons, the ionic size is going to decrease. They're going to get tinier, 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 and tinier, right? I have the same number of electrons, but the number of protons is higher and higher. Okay, now I hope this makes sense so far. Let's talk about ionization energy. So, ionization energy is just the energy that is needed to remove an electron from a neutral atom in the gaseous state. So, for example, when we are making an A plus right here, the energy associated with that process is called the ionization energy. Now, let's think about this. As we go down in a group, we are going to have the loosest electron, so the electron that is the most further away from the nucleus, further and further and further away because our atomic size is increasing. So will it be easier or harder to remove that last electron? It's going to be easier, right? Because it's further and further away from the positive charge of the nucleus. So this means that as I go down in a group, my ionization energy is going to decrease. So it's exactly opposite to the atomic size, which increases as I go down a group. Okay, what happens as I go left to right? Will my ionization energy increase or decrease? Well, because the atomic size decreases, my electrons are going to be closer and closer and closer to the nucleus. So it's going to be harder and harder to take that electron away. I have to put in more and more energy. So my ionization energy as I go left to right is actually going to increase. So again, exactly the opposite to atomic size. What about electron affinity? Electron affinity is simply the energy associated with the creation of a negatively charged ion, just as is shown there, where we created a chloride ion. Now, what do you think? When is it easier to put an electron on an atom? When it's smaller or when it's bigger? Probably when it's smaller, right? Because when you add that electron, it's going to be closer to the nucleus. So again, as we go down in a group right here, we are going to increase the atomic size, but we are going to decrease the electron affinity. So this means that it's actually going to get less negative. Why is it less negative? Electron affinity is generally exothermic, so this is going to give a negative overall energy. Okay, how about if we go left to right? Well, we are decreasing the atomic size, so it's going to be easier and easier to add an electron because the electron that we add is going to be closer to the nucleus. So the electron affinity is going to increase the same way as the ionization energy. But keep in mind that it's actually going to become more negative here. Okay, I hope this makes sense. Let's summarize it on the next slide. As we go down in a group, we know that we are going to add shells, so the atomic size is going to increase, which means that it's going to be easier to remove the outermost electron, so the ionization energy will decrease, and also the electron affinity becomes less negative, so it's also going to decrease. Now, what happens when we go left to right across a period? The atomic size actually going to decrease because we are adding protons, but we are moving within the same shell with the electrons. However, because the atomic size decreases, the ionization energy will increase, and also the electron affinity will increase, which means that it's going to become more negative. So remember that these are just trends. There are always exceptions to these trends. So check out the video on the exceptions to ionization energy and electron affinity trends. Okay, I hope this makes sense. See you in the next video.